Hi, I'm Julian Ritter. Right now I am, and presumably you are too, sitting in my house on a wet rock, surrounded by other rocks, all flying around a massive explosion, which swirls around in a whirlpool of other rocks, explosions, and other dust and stuff, which in turn is surrounded by other balls and whirlpools full of the same type of stuff on what seems to be an infinite plane of otherwise empty space that is expanding quicker and quicker by the minute. Out there seems to be a lot of this dead stuff. It turns out that we're made up of a lot of that kind of dead stuff. According to our best understanding of the laws of physics, that stuff came together and was able to produce us, intelligent life here on Earth. If we're right about that dead stuff turning into us, then presumably it also turned into other stuff elsewhere in the universe, right? I mean, if it can happen here, surely there are other planets that have organisms similar to us in intelligence. But if so, where are they? And how come they haven't popped by to say hello? This question is formally known as Fermi's Paradox. I'll frame it a little better. If we live in a universe where life can come from dead stuff, and that dead stuff can become living and develop a society and get smart enough to leave its home planet, then how come we don't see any signs of alien species doing just that? Better yet, how come they haven't shown up here? So, where be them aliens? Now, there are a few answers to this question, none that have come even close to a conclusive answer. For that to happen, someone would have to pick up the other end of the phone. So maybe we should start by verifying our assumptions. Let's not take for granted the idea that the universe is full of other life. As Neil deGrasse Tyson says, the universe is under no obligation to make sense to you. We figured out some pretty cool and interesting stuff just by sitting down and doing the math. So maybe we should start there. No, don't leave just yet, come on. I promise, it'll be interesting. So, what we're looking to find out is how many intelligent species there are in the galaxy. We'll call this number n. Let's start by looking at our own planet, and using it as a base model for the type of planet on which intelligent life can form. If we start with what we know for sure, we make fewer assumptions, and therefore get more accurate results. First off, we're orbiting around a star. If we measure the rate at which new stars form, we have valuable data which we can use to find other planets around these stars. We'll call the star formation rate R star, and the fraction of those stars with planetary systems around them, FP. Next, we'll find out how many of those planets are Earth-like, meaning rocky planets, in a position around its star that's the perfect temperature for liquid water to form. Scientists call this position the Goldilocks Zone. Not too hot, not too cold, just right. Beyond that, the planet should have an atmospheric composition full of elements that are conducive to organic chemical bonds, things like oxygen, carbon, and nitrogen. We'll call this number of planets Ne. Next, we'll bring in the fraction of Earth-like planets where complex life develops. Call it F1. This is where we get into the weeds a little with our numbers. We don't know much about complex life on other Earth-like worlds, as we've never been out that far. Scientists are doing experiments here on Earth to help us determine the resilience of organic life in extreme conditions, or even in the vacuum of space. These scientists are often called astrobiologists. Anyway, for now, let's just assume that all our variables beyond this point in the equation are speculative, meaning that the information we have is based on educated guesses, computer simulations, and the information we have gathered for the previous variables. Next, we have to find out the fraction of those worlds with intelligent life. This figure presumably should reflect the percentage of life on Earth that we consider intelligent. For example, that includes things like us, certain great apes, dolphins, and other self-aware, intelligent animals. This we'll call Fi. Now, How many of those planets with intelligent life develop into technological societies? Again, we refer to Earth life to inform simulations and estimates. Typically, our answers to this one land in a range. Finally, we estimate the average lifespan of a technological civilization, call it L. We assess this and all other life-based variables in relation to something we call great filters. Great filters are essentially the threats a civilization or species faces in its development. This includes anything that may stop a species from advancing any further in its evolutionary or technological development. For instance, an apex predator hunting a species to extinction would be a filter, as would a global thermonuclear war. Anything that threatens the survival of a species as a whole is a great filter, and a species' lifespan is dependent on its ability to come out the other end of the filter intact. So here is our final equation. N is equal to R star times Fp times Ne times F1 times Fi times Fc times L. Originally derived in 1961, this formula is known as the Drake equation, after its creator, an astrobiologist named Frank Drake. It's a pretty complex equation, but remember, this is a very complex problem that we're trying to solve, and the variables we use are mainly based in probability. Most calculations used by scientists have inputs in ranges rather than specific numbers. One simulation done in 2009 by Duncan H. Forgan outputs a range of potential technological civilizations of about 360 to 38,000, whereas another one done in 2018 by Anders Sandberg and his team estimated that there was a chance higher than 30% that we were the only technological civilization in the entire Milky Way. Now, these results seem kind of vague, but for now it's the best we've got, right? Well, not exactly. While this is one of the more famous equations in the game, some scientists doubt its predictive power. Some others also think that looking for more data on less certain factors is the proper way to go forward, so we can make better predictions and more solid claims, and eliminate some of the guesswork. Enter the Seager equation. In 2013, Sarah Seeger, an astrobiologist at MIT, came up with a different version of the equation, based more on observable phenomena, things she calls biosignatures. Here's a basic rundown of the math. N1, representing the number of planets with detectable signs of life, is equal to N star, the number of observed stars, times FQ, or the number of quiet stars, meaning stars whose surface activity doesn't blur out the view of its planets. It's also worth mentioning that planets near these noisy stars would most likely get baked by the constant bombardment of UV radiation, such that any gases produced by biological life would be destroyed, making detection entirely impossible. We multiply this by the fraction of stars with rocky planets in the star's habitable zone, FHZ, the fraction of those planets that are observable to our instruments, FO, the fraction of those observable planets that have life, FL, and the fraction of those life-bearing planets whose inhabitants produce detectable signature gases, FS. The final equation looks like this. N is equal to N star times FQ times FHZ times FO times FL times FS. Keep in mind, this equation is not intended to give us a clear picture of how many intelligent species there are, but on how many observable planets with life there are. The operative word there is observable. It turns out, looking at stars is a pretty good way to find planets. As a planet passes or transits in front of its parent star, it blocks some of the light, and its atmosphere lets some of that light through. Scientists can then use the spectrum of light that comes from the planet's star as a baseline and use the light that filters through its atmosphere to determine the planet's composition. This isn't the only way that scientists are looking for signs of life, however. Intelligent life with technological civilizations are presumably attempting to do similar things to us, getting out into space, setting up ways of communicating using radio signals, and even looking for other life in the universe. We are using this assumption in our search by looking and listening for these kinds of extraterrestrial radio signals. That's why we have the SETI Institute. The SETI Institute, which stands for Search for Extraterrestrial Intelligence, is a non-profit NASA research organization based out of San Francisco. They have scientists working in every field from particle physics to biochemistry to spectroscopy. SETI's website notes that, quote, there are 100 scientists at the SETI Institute working on nearly 100 research questions, but each of these topics can be related to one of the terms in the Drake equation, end quote. But what we want to know right now is there anyone that wants to talk out there? SETI's primary goal is to look for them, and finding other types of non-intelligent life, while extremely helpful in determining the probability of intelligent life, is not really the same thing, is it? To block out some of the noise and focus on the I in SETI, being intelligence, Yuri Milner started the Breakthrough Listen initiative, a privately funded, large-scale search of the cosmos for radio signals known as technosignatures. On their website, they boast some of the largest and most advanced telescopes and observation techniques available, and they are putting it all towards the search for extraterrestrial civilizations. And they may have found one. Well, maybe. And that's a Jupiter-sized maybe there. See, in late 2020, The Guardian released an article about a radio signal picked up by the Parkes radio telescope when observing Proxima Centauri, our nearest stellar neighbor, between April and May of 2019. The signal is narrow band, meaning that its frequency fluctuations are relatively small compared with most naturally occurring radio frequencies, the type you might find coming from a radio galaxy. This is pretty exciting, although it doesn't automatically mean that the signal is aliens. There are a lot of things in space, probably things we don't know exist, and the signal, while rare, may be caused by something we just haven't seen yet. Or it might come from something we created. Terrestrial interference is what happens when a radio telescope accidentally catches a wayward signal from a radio satellite in Earth's orbit, or some other radio frequency emitting object. Our planetary orbit is so jam-packed with radio transmitter satellites that this frequency was more likely to be caused by someone turning on their car's satellite radio than being first contact. This kind of thing happens all the time. In fact, in 2015, the very same telescope picked up a strange signal they hadn't seen before in space. After some searching, they discovered that the source of the mysterious signal was the microwave oven in the break room. They wrote a whole report on it. You can read it. It's online on Cornell's website. So, not all signals picked up by these telescopes are really calls from ET. What can we say about this signal? Really, it's up in the air. The signal lasted for a total of 30 hours between its first detection and its last, and it was only observed at one telescope. That said, it had some characteristics that got through a few of the more difficult tests. As of now, the signal is known as Breakthrough Listen Candidate 1. Right now, it's a candidate and nothing more. So, where does this leave us in our search? Well, right now we have several organizations working toward the goal of finding other life in the universe. We're also doing simulations and calculations to find out what kind of chances there are for such life to exist. But we've only been looking for about 50 years, and the signals we've sent, like anything in the universe, are constrained by the laws of physics. Any radio signals we've sent out have only traveled about 50 light years since we started. And our galaxy is about 100,000 light years across. Yeah. We might not be hearing back from anyone anytime soon. On top of that, the fact that we haven't been doing this for very long might mean that we just don't know the right way to do it. We don't know the right way to communicate. There might be other ways other civilizations talk to each other that we can't even conceive of yet. Imagine you were trying to speak to all of your friends who use Facebook Messenger by trying to reach them using a telegram. Even more terrifying, perhaps our intelligence level is somewhat common, and a larger, more intelligent civilization sees us the way we see ants. They're out there and they know we exist, but we aren't interesting enough to them to talk to, or we're not a threat, and until we are, they're allowing us to stay alive. This is known as the zoo hypothesis, and one version of it incorporates artificial superintelligence as the most common type of intelligence in the universe. Beyond that, another theory puts more stock in the filters. Remember those? Well, some theorists hold that most of the other civilizations must have been filtered out, and that every civilization must eventually reach its final filter. What that is somewhat of a mystery, but from experience, there are quite a few filters that we've already faced, are facing, and soon enough will be facing, that are pretty convincing candidates. We're still getting a handle on nuclear weapons, we haven't figured out how to stop a runaway greenhouse effect, and we have no idea how to contain an artificial superintelligence once we've created it. Furthermore, there may be things out there that we haven't even considered because we don't know it exists. But we shouldn't let that discourage us. In fact, it's pretty exciting, isn't it? For the first time in our history, we're actually reaching out to the stars to see who else is there. This could be the beginning of our journey to becoming an interstellar species, and since we haven't seen anyone out there, as far as we know, we're the only ones to try. Not bad for a bunch of apes from a wet rock, eh? I've been Julian Ritter. Thank you so much for watching.